Hi, in this video, we want to go through and take a look at some discrete distributions. We're going to look at the binomial distribution and we're going to look at the Poisson distribution. These are distributions that take a look at count data. All right, so here we're talking about we have a mathematical model for some observations that are counts. And we use the mathematical structure of these particular distributions to give us insight into what's going on with our data. Whenever I'm doing anything with statistics, when I'm doing something with data, the more data I have, the less assumptions I need to make. The less data I have, the more assumptions I need to make. So what the situation where we would actually apply these two distributions is where I have count data, and I don't have like a whole lot of data, so that I don't have a whole lot of observations, so that I can just use the data and not worry about the distribution. So we're always kind of like in this balancing act between assumptions and the amount of data we have. All right, so if I've only got, let's say, 30 observations from something, and it might be that those 30 are really expensive to get, but I need to use those 30 observations to gain insight into a situation. Well, what I can do instead, since I'm lacking on data, I take a mathematical model to kind of fill in the details of what's missing. Now, if I'm in a big data situation where I have 10 million observations, I don't need any assumptions. Whatever is in the data is enough for me to figure out what's going on. And so you're always going to be in kind of like this gray area. So you want to make as few assumptions as possible to make meaningful inferences. Sometimes it might be that you can only get like 1 or 2 points of data, and for an experiment, because it's so expensive or so time consuming to get those observations. In that situation, I would probably end up using a Bayesian statistics point of view. We probably won't touch that in this class, but there are methods to kind of fill in the gap. But you would have to be making a lot of big assumptions based off of understanding of what's going on to do that. All right, so let's actually get into this. So I'm taking this code from this author's textbook. I literally just copied and pasted it. Here's the website for his code. You might want to shoot him email saying thank you. It's on GitHub. And you can download the textbook for free from the library. All right, so let's take a look at the binomial distribution. First and foremost, I need to load my packages. You see this percentage PyLab inline? What this will do, this will automatically get NumPy and matplotlib loaded for me, and it'll use the standard abbreviations. That's really nice. It's a little bit faster, so I don't have to have so many lines for import. Now, here is SciPy statistics, because we're going to be using that. So go ahead and load it. All right, so now let's get to the binomial distribution. I use the binomial distribution when I have count data. First and foremost, I have count data. There's a maximum number that I can have for those counts. So if I'm in a situation where I'm modeling the number of passengers in an airplane, and I know the maximum number of seats on that airplane. So let's say it's a smaller plane. I know that there's 20 seats possible, and I want to model how many passengers will be on the plane for like predictive analytics. I might consider a binomial distribution model because there's a maximum of 20. It could be 0, it could be 20 for a given flight. All right, now something that's really important about the binomial distribution is that we make the assumption that our observations are independent of each other, and we have constant probability of a seat being filled or not. Almost always in real life, that does not apply. But the mathematical model, it does a pretty good, a lot of times the mathematical model fills in the gaps well enough for us to go ahead and use the binomial distribution, even though the assumptions don't actually fit for the situation we're in. Vast majority of the time, independence is not going on, but we need to make decisions if we're going to get paid, if we're going to get our paycheck. So we go ahead and just go forward with it. You'll hear some people in, in academics and statistics, harp on, independence and stuff like that. As employees, we need to make a decision. We need to get things out the door. We don't have time to worry about that. We need to get results. And so we always need to be mindful of what assumptions are part of our models, but we're going to be violating those assumptions almost always, honestly. But you always, to make sure that you don't get hit smacked in the face on making incorrect conclusions, you need to know what are those assumptions. So constant probability, independence, count observations, and finally, count observations. Oh, there's a maximum number. So, I'm actually going to type this in. So, because this is important. So, first of all, we have count data. We have a maximum number of count, of count value, maximum count value. We have independent observations. So like in the example of the flight, one seat being filled and another one being filled, those are completely independent of each other. This is almost never the case in real life, but the mathematical model to be 100% correct requires it. So independent outcomes for each 0 and 1. 0, that's the situation where a seat is not filled, and a 1 is where the given seat is filled on the flight example. And next one is, we have independent and, constant probability. All right, so this assumption is saying that the probability that any given seat is filled is going to be constant. It's going to be the same for every single seat. Now, that's not going to be the case because we know that aisle seats are going to be more desirable than middle seats, and window seats are better than middle seats. So, there's other ways to handle that one. But for us, for most of the time, what's going to key us on to using binomial distribution is that we have count values, and there's a hard cap on what is going to be the maximum number that I can get, and I'll know what that number is beforehand. That's important. All right, so now what we're going to do, we're going to use stats. So this is SciPy, using SciPy stats. We're going to use the binom function. So here I'm talking about 20. So I have a maximum of 20, a maximum count of 20, and it's 50-50 on if it's going to be a 0 or a 1. So this is a situation where I have an airplane with 20 seats, and I say that it's a 50-50 chance that each given seat will be filled. And how this is modeled is that so I'm going to make a list of 0s and 1s, and each seat corresponds to a number on that list. If there's no 1 in that seat, it's a 0. If there's someone on that seat, it's a 1. And then this mathematical model will be saying, hey, it's 50-50 for each seat being filled or not. Down here, so once again, I've got 20 seats on my flight. Now here I'm saying it's a 70% chance that each seat has a butt in it. Down here, it's a bigger plane, got 40 seats, and it's 50-50. So let's go ahead and let's generate these. So I'm using the F9 button on Spider. Now K, actually, so let me show you what the output is. BD1. All right, so it doesn't really tell me what's up. Let's take a look at this. All right, so we're taking a look at the stats binom. All right, so this is a binomial generator. So we've created a binomial generator function for us to give us insight into what the binomial distribution. So this generates something for us. So when I use this in a moment, I'm going to have to plug something in to get what I want. All right, so now K, remember I've got A range 40. Let's take a look at what that spits out for me. All right, so I put in 40 into A range. I can see that it makes an array going from 0 to 39. It's a, starting at 0 gives me a length 40 array. Now the next part, I want to use the PMF, probability mass function, for each value of K. So what this is going to spit out when I put this into here, this is going to give me, for the first binomial distribution, first 20 seats and 50-50 chance that there's a butt in that seat. It's going to tell me the probability of no one on the plane, the probability of exactly one person on the plane, probability of 2 people on the plane, probability of 3 people on the plane, all the way up to 39. So let's take a look at what that looks like. And so here, I get this list of numbers, kind of hard to interpret. A lot of digits can spit out me. So when I look at this, first thing, when I start looking at numbers in this format, I want to look at the magnitude. So here it's given something, or it's given scientific notation. So I've got -7, -5, -4, -3, -2, -1, -1, -1, -1, -1, -2. All right, so the largest value is going to be somewhere in the -1 exponent range. What, probably about here. Kind of hard to see, kind of hard to tell what that value is. And then I can see that the numbers get smaller and smaller and smaller until they're practically 0. Well, remember, I said there was a hard cap on the binomial distribution. So when I say that there's 20 seats, I can't have 21 people on that flight. There's only 20 seats available. So once it gets past 20, it's going to be all zeros, because in this mathematical model, anything greater than 20 isn't possible. All right, so now let's go ahead and plot this and just see how these compare. All right, so our first model is in, so we had 20 seats and 50-50 chance that a butt is in that seat. And we can see that it goes up and then comes back down. And I can see that at 10, I have the most likely event. So here, the probability of that is around 0.175. So I have it, so most of the time, on average, we're going to have 10 people on that flight. Okay, well, let's take a look at what happens when we increase it to 0.7. Now, if it's 0.7 for the probability that someone is sitting in the flight, then it's going to be around, let's see, around 14, I think, is going to be the most likely, or going to be like the average. And then if we go from 10, or sorry, if we go from 20 seats to 40 seats, we can see that the average is going to basically double. Actually, it does double. And, but also you see that it's flatter. Like there's a wider range of possible values, not as tall. And so because there's a larger number of seats, I could go all the way up to 40, or I could go down to 0. Well, previously it went from 0 to 20, so it was a lesser range. So I had a higher probability of like 10 at that peak. While here there's more possibilities, so the probability masses get all spread out. Remember, probabilities always add up to 1. They're always greater than or equal to 0. They're always less than or equal to 1, and they always add up to 1. All right, now we want to look at the Poisson distribution. Now, if you're proficient with French, you know that I'm saying that wrong. I actually, before this video, I tried to practice saying it correctly. I couldn't do it. So I'm just going to say it the way I say it. This is a situation where, once again, we're talking about count data. And so it could be 0, it could be 1, 2, 3, 4, 5. What's it? Something about this one is that there's no cap to this. Like, potentially, it could be, the mathematical model is saying that it's potentially could be like any huge number, but realistically, we know that it's not going to go like crazy big. What we're interested in is that we have like no set cap, no set maximum value. For the counts. And we have independence between observations. Those are the critical ones for this model. All right, so what is a good example for this? One that I've worked on was with camera trap data for ecology, trying to figure out, well, how many cheetahs are in a given region of Namibia. It was a project that I worked on. So there, they could have, they set up a bunch of cameras that when there was motion, it would take a picture. And then after a couple of months of leaving the cameras out, they looked at the pictures and they counted the number of times they saw particular animals. So they counted the number of times they saw a giraffe or a hyena or a zebra, and they went through. All right, so in that situation, potentially you could have your counts could be the animal just keeps going back and forth, back and forth, back and forth, back and forth, back and forth past the camera, and it goes click, 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 click. There's no real cap on how many times you can get a count. And because of that, it's how we ended up modeling this, we modeled it with a Poisson distribution. It ended up being a small data situation because they didn't have enough cameras. And so we had to make greater assumptions about the situation that I was really comfortable with the data. But once again, when you have data and people want results, you have to balance it. Am I going to be part of a project and make assumptions I'm not comfortable, I'm kind of gray with? There were things I just said, no, we're not doing that. We're not making this assumption. That's a bridge too far, which didn't go over well. But it's important to me that I give solid models. People who do not have to worry about producing results with data will tell you to just don't build a model in that situation. I find that that's not feasible for those who are in in industry. So I ran the analysis, used a Poisson distribution, got good results. It was a good outcome. So remember, with the Poisson distribution, I have count data. There is no maximum value for the counts. And it's not going to be something like 5 billion. It's not going to be a weird number. And then I have independence between the observations. Now, that last one, in reality, in real life, that never happens. But to fill in the gaps between having, if I don't have big data, I have to make assumptions somewhere. And I go ahead and I accept that mathematical model because that's the best that I can really do. All right, so now, once again, we're going to be using the stats package. So remember, that is SciPy stats is being abbreviated as just stats. And we're going to take the Poisson distribution. All right, so what's going on here? You notice I've just got one number. What I do, I just say, what is the average? That's something that's very nice about this distribution. I only have one parameter. What is the average? And what this is going to do, PD is going to generate, this is going to be a function that generates features of the Poisson distribution for us. And let's go ahead and plot it. All right, so here we can see that around 10 is going to be the maximum value, maximum or the most likely observation I get from this data. So what's saying is that I can see that 0 is unlikely, and then the probability of getting 5 is greater than the probability of 0. And the probabilities keep on increasing as I go up to 10, then they become less and less frequent. Now over here, like potentially with a Poisson distribution, mathematically, any counting number is possible. 1,000,000, 1,000,000,000, those are counting numbers. So potentially under this model, it does have a positive probability. But as you can see from the graph, that probability is so small, I can just disregard it at a certain point. And so here, what we're doing, the probability of being bigger than 40 is so small, I just pretend it's not possible in this model, because that matches the reality of the situation I'm in. Now, something that comes up with this distribution is that the average and the variance are equal to each other. And so if you're unsure about if you should use this, if you see that in your data, your average and your variance are approximately equal to each other, that's a good sign that Poisson distribution is a good choice for you. Yeah. All right, so now let's go ahead and take a look at this again, but let's look at it in a different way. All right, so here I'm looking at the cumulative density function. All right, what's going on here? Remember that values add up from, so probabilities are always between 0 and 1. It's 0 or bigger, 1 or less, and all of the probabilities add up to 1 together. What this is doing, this graph shows me what's the probability of a value or less. So here, that value for 0 is a probability of 0 or less. Well, it's going to be the probability of 0, can't be less than 0. Now here, this value here for 5, that's the probability of 5 or less. So that's the probability of 5 or 4, 3, 2, 1, or 0. When I come over to 10, this is a probability of 10 or less. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, or 0. That's the probability of all of those added up together give me this value. And you can see that as I get more and more values, more and more, as my numbers get bigger, this just gets, this curve goes higher and higher. The probabilities keep on adding together until it's practically 1. It will never actually reach 1, but it gets so close to it as we keep going to the right that operationally, in the data, for those of us who are making reality happen, we can just think of it as being 1, and that's good. Now, this next step is we want to use the lens space function. All right, so what this is going to do, this is going to go from 0 to 1, and it's going to be a length 100 vector. So let's take a look at what this looks like. All right, so you can see that I go from 0 to 0.01010101, and so on, and then here 0.020202, and it keeps on going. This is, if I actually read this out, this is, if I counted all the way through, this would be a length 100 vector. And so it's kind of a weird stepping. Now, let me do this again. I'm going to change this to 101. Let's see how that changes. Oops, that's not what I intended to do. There we go. All right, so now it's a length 101. And now that looks a lot easier. So now it's a lot easier to interpret. So step size is 0.01. So I can see that it's increasing by 0.01 each time. And if I was to go through and count every single one of these numbers, I would see that I have 101 of them. Now 101 Dalmatians, 101 numbers. All right, so now what I want to do, I'm going to take this Poisson distribution generating function, and I'm going to plot some probabilities. All right, so here what we're doing is I'm going backwards. So previously we looked at, given a number, the probability of that or less. So there was a particular number I was looking at. I want to know the corresponding probability. Now I'm going in the opposite direction. I'm taking the probability. What is the number that gives me that probability, or as close to it as possible? And so here, this is going through like a stair step, because remember, it's count observations. I don't have anything in between. I don't have like 1.5. I don't have 3.2. It's always whole numbers. So if I'm interested at, where is it that I would have 0.2 probability? Well, here that's going to be what, 7, something like that. And so I want, so if I add up all of the probabilities of from 0 to 7, I can see that it's going to add up about to 0.2. Kind of interesting to know. So that way I can go back and forth between the numbers and the probabilities freely, and I can get that. Now, this cumulative density function and the this going with the probabilities like this in the opposite direction, I can do this with the binomial densities also that we generated above. We generated 3 of them previously, and I can go back and forth and I can apply all of this. But I just did these few examples just to kind of like give us a taste of it. That's all I got for now. I hope you're staying healthy. I hope you're having fun in this coronavirus world. Take care.